Good evening, Sir Ibarra. Good evening, classmates. I am Rona Jacalinsag and I'm going to report about the Glaze formulation in relation to the journal I've chosen. So for the table of contents, first is the abstract, followed by the introduction, then the objectives, materials and methods, results and discussion, conclusion, and then the references. So for the abstract, the researcher read, gathered, and compared data from the journals. The researcher identified the firing temperatures of the different glazes. Compositions of the different glazes are also listed with their corresponding weight percentage. Glaze ternary diagram for the formulated glazes are plotted. The current work investigated the formulation of glazes using recycled waste glass powder for firing temperatures of 1,100 and 1,250 degrees Celsius. In the introduction, ceramic glazes represent a thin layer of glass applied on the surface of the ceramic artifact to enhance an aesthetic appearance and also to waterproof the product. The smooth surface of the glass layer facilitates cleaning and thus to maintain the hygiene of products such as cups, plates, sanitary vases, and other. Generally, glazes are produced by the application of a suspension of oxides on the surface of the ceramic by immersion, spraying or painting, and fusion by a subsequent heat treatment. As raw materials for the base glaze, mainly quartz, feldspars, and whiting are used. The addition of other oxides such as iron oxide, cobalt oxide, and copper oxide results in the coloring of the glaze. Glaze is a glass that has been modified to melt onto a clay. The chemical name for glass is silicon dioxide. Common names for glass are sand, quartz, and flint. Glass cannot be used alone to make glazes. Glass ceramics are ceramic materials produced through controlled crystallization or the nucleation and crystal growth of a parent glass. The great variety of compositions and the possibility of developing special microstructures with specific technological properties have allowed glass ceramic materials to be used in a wide range of application. I've listed some of the objectives to be looked for in the process. First is to identify the firing temperature range of the glaze. Second, to identify the composition of the glaze. Third, to plot the glaze ternary diagram. Fourth, to make glaze formulation. The chemical compositions of the raw materials used in this work are listed in Table 1. The glass powder was obtained by crushing and milling of transparent glass bottles. The other raw materials were acquired from Minnesota, Brazil. So, the Table 1 shows the composition of the raw materials used in the glaze formulation by weight percentage. So, we have here the components, which includes the glass, the quartz, the kaolin, the dolomite, whiting, and feldspar. And we also have the oxides here listed, the Na2O, the K2O, MgO, CaO, Al2O3, SiO2, Fe2O3, and the LOI. By the way, LOI means the loss of ignition. In the material and method, two glaze compositions, namely the sample 1 and sample 2, are indicated for a firing range of 1,250 degrees Celsius, which falls under the mid-fire range. The third composition, sample 3, indicated for a firing temperature of 1,100 degrees Celsius, which belongs to the low firing range. Sample 3 contains lithium carbonate and borax to lower the melting temperature. The compositions are listed in Table 2 to 4 in weight percent and also in the molecular unity formula or the CER formula. The unity formula shows the relationship between the number of molecules in the three categories, the fluxes, stabilizers, and glass formers, or the aka RO/R2O, the R2O3, and the RO2. From this formula, one may deduce the surface characteristics, the melting range, and color response of a glaze. So the table 2 shows the composition of sample 1 fired at 1250 degrees Celsius. So in the left side shows the composition by weight percentage, and for the right side shows the molecular unity formula. So for the composition, the glass powder has 27.8 percentage, and for the quartz, 28.5%. The dolomite has 0.2%. The zinc oxide has 4.9%, and the kaolin for 25.5%, a total of 100%. And for the molecular unity, here shows that the Na2O has 0.22, the K2O has 0, the MgO has 0.2, the CaO is 0.57, the ZnO is 0.12, and for the alumina we have 0.34, the SiO2 is 3.13, the P2O5 is 0, the TiO2 is 0.01, the Fe2O3 is 0.01. Same goes for the table 3 for the composition of sample 2 fired at 1250 degrees Celsius. The glass powder has 23.1%, the quartz has 25.5%, the dolomite has 13.9%, the zinc oxide has 2.8%, the kaolin has 34.7%. And for the molecular unity formula, or the CER formula, we have the Na2O of 0.21, the K2O for 0, MgO for 0.24, CaO for 0.42, ZnO for 0.12. The Al2O3 is for 0.50, SiO2 has 3.40, P2O5 0, TiO2 0.1, Fe2O3 0.1. And for the table 4, it is the composition for sample number 3 fired with 1100 degrees Celsius. For the glass powder, it has 15.2%, the quartz has 30.3%, the whiting has 4.5%, the kaolin has 22.7%, the lithium carbonate has 7.6%, and the borax has 19.7%, a total of 100%. So for the molecular unity formula, the Na2O is 0.34, K2O is 0, MgO is 0.01, CaO is 0.27, Li2O 0.38, the Al2O3 0.35, B2O3 0.38, and for the SiO2 3.40, TiO2 is 0.01, same goes for Fe2O3, which is 0.01. Figure 1 shows a graphical representation of the compositions of the 3 glazes prepared. The 3 axes shown are in analogy with the CER formula, plotting the Al2O3 and SiO2 content, while the third axis represents the whole amount of the alkali and alkaline earth metal oxides. So the upper part is the 100% Al2O3, the right part is the 100% SiO2, and the left side is the 100% flux. So the samples were fired in an electrical furnace at 1250 degrees Celsius or 1100 degrees Celsius with a heating rate of 2 degrees Celsius per minute and an isothermal holding time of 1 hour. So they only differ with their firing rate and their composition also, and also their CER formula. So table 5 shows the CER formula of formation. So we are already given the values of the CER formula, and by this calculation, we are able to confirm that the values given are of the same values that are calculated here. Table 6 shows the sample 1 oxide analysis. By here, you're given the fluxes, and it is described here, given the Na2O, the MgO, CaO, ZnO. Also the stabilizers, which includes the Al2O3 and Fe2O3, and the glass formers, the SiO2 and TiO2. For sample 1, it has a total fluxes with the Na2O equivalent to 0.5857, the MgO for 0.0784, the CaO for 0.4012, the ZnO for 0.0027. And for the stabilizers, Al2O3 has 0.89651666 and the Fe2O3 for 0.01. For the glass formers, SiO2 has 6.84986, the TiO2 for 0.01. Table 7 shows the sample 2 oxide analysis, which was also fired with 1250 degrees Celsius. And this shows the fluxes here, the stabilizers, and also the glass formers. Na2O has 0.99659, MgO with 0.00141, CaO with 0.00093, ZnO with 0.00106. For the stabilizers, the Al2O3 has 0.02125, the Fe2O3 with 0.01. For the glass former, SiO2 has 1.0603, the IO2 has 0.01. Table 8 shows the sample 3 oxide analysis, which was fired with 1100 degrees Celsius. And by given the percent composition, we are able to obtain the fluxes, stabilizers, and glass formers. For the fluxes, the K2O has 0.11515, the Na2O has 0.17781, MgO has 0.26355, the CaO with 0.43873, LiO2 with 0.00296. For the stabilizers, Al2O3 has 0.1558199, B2O3 with 0.00428. For the another stabilizer, the Fe2O3, 0.0152018. And for the glass formers, SiO2 has 1.01894825, and the TiO2 with 0.015201754. The appearance of the glazes after firing can be observed in Figure 2, Sample 1 or the BG1, and the Sample 2, which is the T2, fired at 1250 degrees Celsius, and in Figure 3, Sample 3 fired at 1100 degrees Celsius. After firing, Sample 1 and 2 showed no crazing or other failures, indicating that the thermal expansion coefficient of the substrate and the glazes are similar. Both glazes have a smooth appearance, while Sample 1 being transparent and Sample 2 slightly matte. Figure 3 shows the Sample 3 T1 with a glaze after firing at 1100 degrees Celsius. The glaze sample 3 developed for a lower firing temperature of 1100 degrees Celsius exhibited no defects, exhibiting a shiny and smooth surface but also slightly matte, similar to glaze sample 2. For the conclusion, first, two base glazes, sample 1 and sample 2, for a firing temperature of 1250 degrees Celsius, and one sample 3 for a firing temperature of 1100 degrees Celsius have been developed. The base glaze sample 1 was of a completely transparent and shiny surface, while sample 2 and sample 3 had a slightly opaque surface. In all cases, defects such as crazing and crawling were not observed, indicating that the thermal mismatch between the glaze and the firing ceramic body was very small and tensions in the glazes were kept to a minimum. Finally, this work demonstrates that it is possible to use waste glass in the production of ceramic glazes by an adequate adjustment of the glaze compositions to the ceramic body in order to avoid defects caused by the different thermal expansion coefficient of the glaze and the ceramic. Another very important factor to be considered is the intended firing temperature of the ceramic ware. It is easier to develop high firing glazes because the fusibility of the glass increases with increasing temperatures, and the necessary adjustments of the composition are simpler to achieve. The amounts of waste glass used in the base glazes sample 1, sample 2, and sample 3 were 27.8, 23.1, and 17.5%, respectively, demonstrating that the viability and potential of recycling glass in this way. The benefits of using recycled glass in the glaze formulation are the substitution of the natural resources of quartz and especially feldspar, besides to open up alternative ways of glass recycling. In this way, industry but also craftsmen may profit in recycling glass. Here are the references used in this study. Thank you for listening and I hope you learned something.